Most time series wins are just future leakage. Fix it by building lag plus rolling features the right way in 5 minutes. This is the workflow you'll know how to run when we're done, which builds leak-free lag and rolling features and evaluates accuracy with forward time splits. I'm Professor Pi, teaching AI foundations with simple Python. Time series projects fail when models peak at the future. That sneaky peak looks like a great score in development and a disaster in production. What you really need are features that only use the past and an evaluation that mimics real forecasting. Success is predictable. Stable forecasts on new dates and scores that match what you will get live. At a high level, lag features copy past values forward in time, so each row only sees history. Rolling features smooth past noise by averaging a controlled window of previous values. Together, they give models memory and stability without leaking tomorrow into today. We will build a tiny, realistic daily series. Create 1 day and 1 week lags. Add a rolling average, and then validate with true forward time splits. No magic math, just pandas, NumPy, and a time-aware validation loop. So our numbers mean something. Now we create the toy series. This snippet builds a seeded daily pandas time series with trend, seasonality, and noise. It starts by importing NumPy and pandas, then fixes randomness with NumPy seed to keep results reproducible. The variable y combines a linear trend, a smooth sine wave, and small Gaussian noise to feel realistic without being messy. A pandas data frame named df is created with a daily date-time index labeled ds, so time-aware operations behave correctly. That index will anchor all future lag and rolling calculations. The final print shows the total number of rows and the last date, confirming the stable, ordered foundation we'll use for leak-free features. Next, we create simple, lagged predictors. This example creates past-only predictors using pandas shift to prevent data leakage. The column yLag1 means y from yesterday, while yLag7 means y from a week ago. Both safely moved backward in time, so the model cannot peek ahead. The function shift is the key primitive here, aligning each row with strictly historical values. Because the first few rows lack complete history, dropna removes the warm-up period, producing df2 with valid training examples. The variable firstDate captures the first index, where both lag features exist. The printed start date confirms we begin modeling only once the lags are fully available. Now we test those lags as baselines. This code compares 2 simple leak-free baselines using pandas data and NumPy math. The variable yTrue holds the actual target, and we build forecasts by reusing yLag1 and yLag7 as predictions. NumPy's mean and abs functions compute each model's mean absolute error, a practical accuracy metric that behaves well on noisy series. The variable best picks whichever lag delivers the lower error, giving a quick ranking without training a full model. This comparison acts as a sanity check. If lags cannot beat naive guesses, something's off. The printed best value shows which historical anchor is more predictive here. Next, we add a smoothed pass signal. This snippet adds a smoothed pass signal by computing a rolling mean on a shifted series with pandas. The variable roll is built from y shifted by 1 step, then averaged over a window of size w, ensuring every value only uses history and never current or future observations. The data frame df3 keeps y, existing lags, and the new y roll feature, dropping rows until the window is fully available. We then measure its mean absolute error as a 1-line forecast. Increasing w smooths noise more, but adds lag, which can dull responsiveness. Decreasing W reacts faster, but may be noisier. The printed error quantifies this trade-off. Finally, we test these features under realistic time splits. This example trains a scikit-learn linear regression with time series split for walk-forward validation. The matrix X uses Y lag 1 and the smoothed Y roll, while Y holds the target. The object time series split creates chronological folds that respect ordering, and its split method yields expanding train and forward test indices. For each split, linear regression fits on past data and predicts the future slice, and NumPy computes the mean absolute error. The list MS stores fold errors, and their average summarizes baseline performance without leakage. The printed CV May shows forecast accuracy under realistic, time-ordered evaluation, confirming the features and validation logic are production safe. In a real project, you would map the toy index to your event timestamp and use the same shift and rolling logic per group if you have multiple entities. The pattern stays identical. Create past-only features, drop warm-up rows, validate with forward folds. Recap: lag and rolling features give models memory without leakage. Use them when you forecast ordered signals and need reliable live performance. Caveat: early rows lack history, so you must drop warm-up periods or handle them separately. Next step: tune the rolling window size to trade off noise reduction against responsiveness and rerun the time split validation to see the real impact. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.